My dear friends, this video lecture is about how to expand the given analytic function f of z as Taylor series expansion. Right? Now the statement is, if f of z is analytic at all points inside a simple closed curve C, here it is called a circle with its center at the point E and the radius R, then at each point Z inside the circle C, the function f of Z can be expressed as this format. The function f of Z is equal to f of A plus Z minus A whole power 1 by 1 factorial f dash of A plus Z minus A whole square by 2 factorial into f double dash of A plus etc. etc. Now, in the third type, there is a next derivative, that is Z minus A whole power 3 by 3 factorial f third derivative of A. So, generally, summation n equal to 0 to infinity Z minus A whole power n by n factorial into f nth derivative of A. We substitute n equal to 0, we get the first term. Putting n equal to 1, we get the second term. Putting n equal to 2, we get the third term. So, summing up. So, this is the expansion is known as Taylor series. So, Taylor series expansion is nothing but an analytic function can be expressed in terms of the points in powers of Z minus A about a single circle. Where this n in Fn of A denotes the number of derivatives. So I'm going to repeat this. Taylor series expansion is nothing but an analytic function f of Z can be expressed in powers of Z minus A, where the point A is inside a circle. Right? So, already we have come across some familiar infinite series. Let us see one by one. So, these are the some infinite series, and you know 1 plus z whole power minus 1 is a binomial expansion. 1 minus z whole power minus 1 is also binomial expansion. Power minus 1, right? Power minus 2 means this is the binomial expansion. If plus and minus comes alternatively, then both the terms minus 1 whole power is a power. If both are minus, within this positive term. Power minus 2, then again plus here, plus minus comes alternatively. Then 1 minus 2 z plus 3 z squared minus 4 z cubed, etc. etc. If both are minus sign, all are positive terms. These expansions 1, 2, 3, 4 are called binomial expansions when not z is less than 1, strictly less than 1. Fifth one is e power z is an exponential function. It's in powers of z. So the answer is 1 plus z by 1 factorial plus z squared by 2 factorial plus z power 3 by 3 factorial, etc. etc. Finally, z power n by n factorial. Where n is any one, or z is any value, this is true for any values of z. That means that not z less than 10. So suppose the power, the exponential power is minus, then it becomes plus minus plus minus. Because replace z by minus z is going to minus. Then minus z whole square becomes here plus. Minus z whole 3 is minus 3. Right? So these are some standard results we have already come across without knowing that some Taylor series expansion is already available. Now, in this, hello friends, the first problem in Taylor series expansion. Question number 1. We expand f of z is equal to e to the power z in a Taylor series about z is equal to 0. So given function is e to the power z. Find f dash of z is again e to the power z, f double dash of z again e to the power z. The point is given here as 0. Substitute z is equal to 0 in f of z, f dash of z, f dash of z, we get 0, 1. So e4 0 is 1, e4 0 is 1, e4 0 is 1. Now what is the Taylor series expansion of f of z about the point A? This is the formula, right? This is the formula, f of z equal to f of a plus z minus a by 1 factorial f dash of a plus z minus a whole square by 2 factorial into f double dash of a. In this problem, the point is 0. Substitute a equal to 0. Substitute a equal to 0. Substitute a equal to 0. We already found the f of 0, f dash of 0, f double dash of 0 values. Substitute, we get this is the required Taylor series expansion about the point u equal to 0. So what's the point u equal to 0? So it is in powers of z square. Suppose point is a means is z minus a equals square. Right? See the second example. Expand f of z is equal to sin z about z equal to pi by 4. So in this problem, the point is pi by 4. So you expect the answer in powers of z minus pi by 4. Understand? Now what is f of z? Sin z. Find the derivative. First derivative is cos z, second derivative is minus sin z, third derivative is minus cos z. The point is pi by 4. So substitute the point, f of pi by 4 1 by root 2, f dash of pi by 4 1 by root 2, f double dash of pi by 4 minus 1 by root 2, f triple dash of pi by 4 is also minus 1 by root 2. Now substitute this value in the Taylor series expansion. So as already we know that the Taylor series of f of z about the point z equal to a is this case. Substitute a equal to pi by 4. Got it? Pi by 4. So it is in powers of z minus pi by 4 now. What about f of pi by 4, f dash of pi by 4, f double dash of pi by 4? It is, we have found in the previous slide, 1 by root 2, 1 by root 2, minus 1 by root 2, minus 1 by root 2. Now substitute this, we get. I feel that 1 by root 2 is common. So when you take 1 by root 2 is common, you get 1 plus z minus pi by 4 minus z minus pi by 4 whole square by 2, etc. etc. Right? Where this case is missing. Okay. So this is the Taylor series about the point z is equal to pi by 4. So powers of z minus pi by 4. Powers of z minus pi by 4. Thank you. Hello friends. This is the third problem in Taylor series. Inside a single circle. Say this problem. Solution A is show that 1 by z square is equal to summation n equal to 0 to infinity n plus 1 into z plus 1 whole power n, when mod z plus 1 is strictly less than 1. And the second subdivision is 1 by z square 1 by 4 sigma n equal to 0 to infinity minus 1 whole power n plus 1 into z minus 2 by 2 whole power n, then z minus 2 mod z minus 2 is less than 2. See that The left hand side is the same, 1 by z square. But there are two different expansions. Why? Because the region is different. This is known as a region of convergence. Here mod z plus 1 less than 1. That means the circle whose center is 2 minus 1, the radius is 1. The second question, the region of convergence is mod z minus 2 less than 2. The circle whose center is 2, the radius is also 2. Let's see the solution. First of all, the section V, solution V, 1 by z square. So for 1 by z square function, we add and subtract by the constant term 1. Because the first solution is, the circle is mod z plus 1 less than 1. So I need z plus 1 term. So for the convenience, we add and subtract the constant 1. Now just take the minus sign outside, we get 1 minus of z plus 1 whole square. The square of minus 1 becomes plus. So this terms, when we bring the numerator side, this becomes power minus 2. So this looks like a binomial expansion. So here this is my z. When we expand the binomial expansion, only when the mod z value is less than 1. So what about mod z plus 1 less than 1? Yes, correct. So given that the region of convergence is mod z plus 1 is less than 1, so we apply this, looks like a binomial expansion. Minus sign, minus sign. Here minus, here minus. So everything is positive. So 1 plus 2 times z plus 1 plus 3 times z plus 1 whole square plus etc. etc. So generally, sigma equal to 0 to infinity, n plus 1 z plus 1 1 because the region of convergence is z plus 1. So we get this in powers of z plus 1. What about the second circle? The second circle is mod z plus z minus 2 is less than 2. Mod z minus 2 less than 2. We use normally the binomial expansion. All the binomial expansions are valid only when mod z less than 1, right? So I want to divide this by 2 on both the sides. We get mod z minus 2 by 2 less than 1. Correct? So now 1 by z square is equal to 1 by add and subtract by 2. Add and subtract by 2. So z minus 2 plus 2 whole square. So this 2 can first. So 2 plus z minus 2 whole square. When you take the 2 outside, becomes 1 by 2 square is 1 by 4. Then this term comes 1 plus z minus 2 by 2 equal to 2. Now again, this looks like the binomial expansion. 1 plus z whole power minus 2. So here plus sign, here minus sign. The plus minus comes automatically. Here z minus 2 by 2 is the z term. So by using the binomial expansion, we get this series. So that's why 1 by z square is 1 by 4, sigma n equal to 0 to infinity minus 1 equal to n plus 1 into z minus 2 by 2 power n. So the same function can be expressed as a Taylor series based on their region of convergence. So the region of convergence here play a vital role, right? So Taylor series expansion about your point inside a circle, we have seen it. What about in between the circles? That is the next lecture. Hello. This is the last type in Taylor series expansion. We expand the function in between the two circles. In between the two circles, this type of questions may ask in part C. 12 marks category. Let us see this problem. Expand the function f of z is equal to 1 by z square minus 3z plus 2 in the region 1 strictly less than mod z less than 2. This is nothing but a concentric circle is above the radius 1, below the radius 2. The smaller circle is mod z less than 1, the bigger circle is mod z less than 2. So this between the radius 1 and 2. This is often called as a region of convergence. A region of convergence. So based on, depends on the region of convergence, we may express this function f of z. Now our first job is to split up this into two linear factors, and by using the method of partial fractions, once again we express f of z is equal to 1 by z minus 2 minus 1 by z minus 1. After getting the a and the b value with the method of partial fraction. You see, this is the function method. I want to use the given region of validity, and at the same time let us rearrange this f of z, into the binomial expansions. When the binomial expansions are valid, only when mod z value is less than 1. Got it? Mod z value less than 1. So let us use the given region to find the region of validity. Given region. So given region is 1 less than mod z less than 2. It is split up into two circles. Yeah, 1 less than mod z, that is outside the smaller circle with the radius 1. And the one is mod z less than 2 inside the bigger circle with the radius 2. Right? So divide this by z, we get mod 1 by z is less than 1. Divide this by 2, we get mod z by 2 less than 1. So when the regional validity, we found that mod 1 by z less than 1, mod z by 2 less than 1. So when the binomial expansions are valid, mod z is less than 1. So here, with the given region, we found 1 by z and the z by 2 are less than 1. Now rearrange the f of z in terms of 1 by z and the z by 2. So that's the concept. So this is my f of z, 1 by z minus 2 minus 1 by z minus 1. So we have only two regional validity, that is z by 2 and 1 by z. Alright. So let us take the minus sign front, we get 2 minus z, and once again take the 2 outside, we get this 1 by z minus 2. 1 by z minus 2. 1 minus z by 2. 1 minus z by 2. So what about z by 2 mod is value less than 1? Why it is z is coming in the numerator, why it's coming in the denominator? What is the reason? Yeah. This is the inside the bigger circle, this is the outside the smaller circle. So smaller circle means z in the denominator, negative powers of z. Inside means it is positive powers of z in the numerator. Got it? That's the concept. So here, minus 1 by 2 outside. This is 1 minus z minus 2, 4 minus 1. Looks like a binomial expansion. So binomial expansions are valid only when the z value is less than 1. Yeah, here mod z by 2 is less than 1. So this is 1 plus z by 2 plus z by 2 plus 1, etc. etc. Z by 2 Then the second term, take the z outside. Because we have 1 by z is the second region of convergence. So we rearrange this term, the second term, to get in terms of 1 by z. So I can take z outside. The first one I took 2, second one is by z, because I have z by 2 and by z. Correct? So from this we get z outside we get minus 1 by z into minus 1 minus of 1 by z over minus 1. Yeah, this is also a binomial expansion. So we get this series minus 1 by z into 1 plus 1 by z plus 1 by z whole square, etc. etc. 1 by z over n. So final answer is minus 1 by 2 sigma n equal to 0 by infinity z over n by 2 for n minus 1 by 2 sigma n equal to 0 by infinity 1 by z over n. Multiplying 2 to the term z over n plus 1, multiplying z to the term z over n plus 1. Minus minus is common, taken outside, nothing here minus is missing. Then sigma n equal to 0 by infinity z over n by 2 for n plus 1 plus z n by z over n plus 1. So one term is in the numerator, is a positive power, one is the denominator, is negative power. Why? Because this is f of z can be expressed between two circles, one with having the radius 2, so inside the bigger circle and outside the small circle. So outside means this z is the denominator, negative powers of z. Inside means positive powers of z. Got it? So this is the part C type question under the Taylor series expansion. Thank you.